There, class. So we're just going to start our recording for today. This is going to be lesson 2, properties of exponential functions. So in this lesson, what you're going to be exploring, you should have already done this as an investigation. When you're opening up this video, it should purely be to see what your answers are. You can even, before you watch the video, you can go and just look and see if your answers are correct in the lesson. You can look at the solutions, and if they're correct and you kind of just understand it, like that's perfect. You don't need to go ahead and watch this video. But if you're kind of stuck and you don't understand how to do a certain of the things, right? You would be able to watch this lesson for that, right? So we're just gonna get started with our first kind of uh, investigation here. So we're going to be looking at three functions, right? So we're going to be looking at the similarities and the differences between y equals 2x, y equals 2x squared, and y equals 2 to the power of x, right? So it says to graph each of the functions using the table of values provided or using Desmos. So I personally use Desmos. And I did a table of values just so that you could both see them, but I just wanted a rough graph, right? And also calculate the first and second differences for each. And I actually added a separate column for y to the power of x. So you'll see on yours, just say y to the power of 2x, right? And I added a separate column because that one's going to have the constant ratios as well. Okay. So when we remember, if you remember back to grade 10, or even grade at the beginning of this semester, our first and second ratios are going to be um, just you take the y. So the first differences are just each difference between the y. So -4 minus -6 is 2. -2 minus -4 is 2. 2 minus -2 is 2. It's just the differences of consecutive y values. So that's our first differences. Our second differences are just the differences between the first differences. So 2 minus 2, 0. 2 minus 2, 0. 2 minus 2, 0. 2 minus 2, 0. 2 minus 2 is 0. So you'll notice here for something like y equals 2x, which we know is a linear function, right? The first differences are going to be consistent, as well as they are second differences are going to be 0. Right, so this is what our linear function looks like. I'm just going to highlight it in this pink highlighter so that you know what it looks like. And you know that it corresponds with that y equals 2x. So now if we go and look at 2x squared, right, we're going to go and find the second differences here. So we're going to do 8 minus 18, which is -10. I'm just going to go ahead and write them in. You should have already done this math, but if you haven't, pause it here and try it by yourself. Right, and then the second differences are going to be 4, 4, 4, 4, 4. So you know that for a quadratic function, the second differences are consistent. They're all the same. So notice how they're all 4 here. And that makes sense because our quadratic function is this blue function right here. Right? Just going to go highlight this in blue. As well as just let, maybe we'll just write over here that this is y equals 2x squared. Okay. So then you're going to do the same thing for the next ones, right? You're going to have y equals 2x. So now your x is actually going to be your exponent. So you're going to put in 2 to the power of -3, which I already wrote in, gives me 0.25, 0.125. To the power of -2 is going to be 0.25. And then what I'm going to do is I'm going to just go find the first differences. So here it's going to be sorry, 0.125, right? 0.25, 0.5, 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4. Notice how they're not the same. And if I was to go and actually find the second differences, they wouldn't be the same either. So you'll notice that here, right? My form is terrible sometimes, but you get the idea, right? But if I was to actually go find the constant differences, so I'm actually going to erase these. If I was actually to go find the constant ratios between the y's, so if I was to take 25 and instead of minusing, I was to divide them by each other, right, I would get 2. 5 divided by 0.25 is also 2. 1 divided by 0.25, 2. 2 divided by 1, 1. 4 divided by 2, right, is going to be 2. Yeah, this should be 1. This should be 2. 2, 4 divided by 8, 2. Right, so the constant ratios are y2 divided by y1. Okay, and notice how here the constant ratio 2 is also the base of this function. So you can actually find the base of the function by just looking at the constant ratio. So it says, can you describe any similarities or differences? So we're just looking at the graphs here. All three of these, if you look at the equation, have a equals 2, right? So they're all vertically stretched by 2. They all have a point at 1 equals 2. So you'll notice 1, like right here, they all kind of intersect at that point. Right. The difference is that number 1 has negative y, so you'll notice that number 1 goes into the negative quadrant. Number 3 never actually touches the x-axis. It has an asymptote, right? And then number 2 is because you can't have 2 to the power of, even 2 to the power of 0 will give you 1, so you can never have a y of 1. Right? If you look at the shape, they're all different shapes. Number 3 has an asymptote. Number 2 opens up only, right? So number 1 is the only one that had those. The linear is the only one that has those x values. Okay. So any similarities in the first and second differences? So quadratic functions all have a second difference that is constant. Linear functions all have the same constant first differences, and exponential functions have the same constant ratios, which also is their base value. Okay, so if we were to find the domain and range, if we go look at y equals 2x, there's no restrictions in what the x can be. There's no restrictions in what the y can be. So we know that the domain here is x is an element of all real numbers. Same idea with the domain, or sorry, the range, y is an element of all real numbers. For this one, again, if you look at this function, there's no restrictions on what the x can be. But there is a restriction on what your y can be. Because this has a maximum here at 0, 0, it has to open upwards, which means that your y can never be less than 0. So y such is an element of all real numbers such that our y always has to be greater than or equal to 0. On the flip side here, you'll notice that there's no restriction on what the x can be. So here, the x is an element of all real numbers, right? But there is a restriction on what the y can be. The y can't be 0. And it can't be less than 0, right? Or it can't be less than 0 because even if you had a negative exponent, notice how we still get a positive y value, right? So then it means that y such that y is greater than, not greater than or equal to. So be careful here. Greater than is different than greater than and equal to. It actually can't be equal to 0, right? Because it doesn't cross that. There's an asymptote there. So it's y is greater than 0. And that's going to be our range. And that's kind of the typical ranges. And then when we go into transformations of those functions, they change. Okay, so for the next one, what you were going to graph is you were going to go ahead and compare the b is greater than 0 in all of these, right? So I'm just going to go ahead and put in our values here, right? I already put them in. Again, if you're looking for first and second differences, we're just going to go ahead and plot them in. So again, first is just y2 minus y1. Oops, sorry. And I knew that that's what it was going to be because it's an exponential function. So I won't have constant first differences, right? But I will have constant ratios. And just by looking at this, I know that my constant ratio is going to be 2, right? So if I took 0.5 divided by 0.25, it's going to be 2, 2, 2, 2. And another way that I could have seen that is because my base of this function is 2. Okay? Here, 0.25 divided by 0.6 is going to give me 4, right? 1 divided by 2.5 is going to 0.25 is going to give me 4. 4 divided by 1 is 4. 16 divided by 4 is 4. Again, that makes sense because my constant ratio is my base, right? And then for this one, again, I just plugged it in and I found the constant ratios. 7, 7, 7 divided by 1 is 7, 49 divided by 7 is 7, right? And again, makes sense because my constant ratio is a 7. Right, so then I just went ahead and I graphed these in using Desmos. Again, you can use Desmos, you can use like the actual points. Either way, you'll get the same answer. And so this one you can see it says asking how are the graphs similar. So an exponential function, you'll notice that they are all exponential. They all have an asymptote of 0, right? So it gets really close to the 0, but it never actually touches it, right? And they're all increasing. So see, as the x gets larger, so does the y. They're all growing in that direction. Okay. How are these graphs different? Some of them are increasing faster. So you'll actually notice that compared to the y equals 2x, the y equals 4x, and the 7x, the larger the base is, so the larger the, sorry, this is just such bad form. Should be up here. The larger the base is, so the larger our big number here is, right? The steeper the increase. So the more of a curve, the more growth is happening in a smaller increment of time. Okay, so that's something that you can mention there, right? The constant ratio tells us the base, the value of the base. So just like the constant ratio was 2, so the base is 2. Constant ratio was 4, base is 4. Constant ratio was 7, base is 4. 7, sorry, right? And increased base means that it's a steeper growth, right? So something that was growing using this model is growing slower than something that was using this one. So just the larger the base, the steeper the growth, or whatever it could be, right? And if we compare this back to our R naught value, that makes sense. The higher the R naught value of a virus, the faster it grows and spreads. Here I just put in the functions, domain and range. All of them have the same domain and range, right? They all have x such as x is an element of all real numbers, right? And the x is greater than 0, not greater than or equal to. Something to keep note of. And it's asked what the x-intercept for each of these graphs is. There is no x-intercept because it doesn't cross the x, right? They're never going to be x equals 0. It's always going to be greater than. And the y-intercept here is actually going to be y is at 1, because if you put in 0 for x, right, you're going to have, that shouldn't be 1, should be comma 1, right? If you put in that value for x, 0, because at the y-intercept, 0 is equal to x, and it's always going to be 1 because anything to the power of 0 is going to be 1. Okay? Now, that's if your b value or your base is greater than 1, which means that it is a positive number, right? And it's greater than 1. Now, what if your b value is actually in between 0 and 1, which means it's not necessarily a negative, but it is a positive number, but it's a fraction or a decimal less than 1. Okay? In this situation, you're going to do the same thing. Let's go ahead and plot these points. So I actually went ahead and wrote them down and I drew them in Desmos again. So then I have, I'm not going to do the first differences because they don't really matter. I'm just going to go ahead and do the constant ratios. So 2 divided by 4 is 0.5. 1 divided by 2 is 0.5. 0.5 divided by 1 is 0.5. 0.25 divided by 0.5 is 0.5. Right? And if I think about that, 0.5 is also 1.2, so that makes sense. The constant ratio is the base. Here I did the same thing. I actually did find the first differences, but I don't care for them right now. I'm just going to go ahead and say, okay, 3 divided by 9, 1 over 3, 1 divided by 3, 1 over 3, 1 over 3 divided by 1, 1 over 3, 1 over 9 divided by 1 over 3 is going to give me 1 over 3, which makes sense because that's my base. Same idea here. You're going to have a constant ratio of 1 over 4. Right, and if you graph these out, you'll notice that your graph that is representing 1 over 4 is going to be this blue graph, 1 over 4 to the power of x. The red graph is going to be the one that represents the 1 over 3 to the power of x. And the green graph that we have here is actually the one that is 1 over 2 to the power of x. So there you have your 3 graphs. And if you were going to explain these to someone, they're all exponential functions. They all also have an asymptote of 0. They slowly approach 0, but they never touch it, right? The thing is now instead of increasing exponentially, they're actually decaying exponentially. So as the x gets larger, right? As you get larger in x, the values of y are actually plummeting. So they're actually decreasing. So this is what we call exponential decay. So for a b of greater than 1, we say it's exponential growth because that makes sense. They're growing, right? And then for b of x is in the middle, we say it's exponential decay. So if it's between 0 and 1, okay? And another thing to notice is that the smaller the fraction, so 1 over 4 versus 1 over 2, 1 over 4 is a smaller fraction. The smaller the fraction or the smaller the decimal, that means that the base is smaller, the faster the decrease is. So this is the opposite. Normal, when we notice that the base was higher, it was going to be a higher growth rate, versus here, if the base is smaller, it's a faster decay. Constant ratio tells us the value of the base. Again, decreased base means steeper decay, right? And here our domain and range actually should the same. So they are x. X is an element of all real numbers, right? Y is an element of all real numbers, and we still have an asymptote at that 0. So it's going to be y is greater than 0, right? Greater than, not equal to. And they all have the same. The only time that these change is, say, when you're determining, I don't know, time, right? And if you can't have a negative time, that means your element of XER changes, right? For Y, if you have a translation down, right? Or for X, if you have a translation to the left or the right, now your values change, right? So you just have to be careful with that. But your domain always changes according to your translations, your vertical shifts, okay? What is the x-intercept? Again, there is none because there's no translation. So if there's no translation, there's no x-intercept. An asymptote is a line that the curve approaches more and more closely but never touches. In this case, it's y equals 0. And it's always y equals 0 unless there's a translation, and we'll talk about translations. This is just kind of a summary of what we learned. So an exponential function in the form is the form y equals b to the power of x, where b is the base. So sometimes you have 2 to the power of x, sometimes you have 7 to the power of x, b is just the base, and x is the exponent. Y equals bx always passes through the point 0, 1 unless there's a translation, right? The domain is always going to be y. X is an element of all real numbers, again, unless there's like a real life problem that can exist, right? And the range is always going to be y is an element of all real numbers such that y is greater than 0, not greater than or equal to, just greater than 0. Again, unless there's a translation. No matter how small you make x and y, it'll never equal to 0 unless, again, there's a translation. And the graph will just get closer and closer to the x-axis, but it will never touch it. When there's a translation, the asymptote actually translates up and down as well. There is no x-intercept. The x-axis in this situation is called an asymptote for the function y equals bx. If b is greater than 0, then we'll say that something is exponentially growing. So you'll see here, right? As the x values go up, so you'll see. As the x values go up, so do the y values, right? In this situation, as the x values go up, the y values actually come down, right? So that's what we call exponential decay. So this could be something like y equals 2 to the power of x, and something like this could be y to the power of negative 1 over 2, or 1 over 2x, right? So where x is a fraction or a decimal, and then versus y to the power of 2x, where b is greater than 0. Right, and that's it for this lesson. Make sure that you at least try it by yourself. There is homework questions. Use Desmos to do number 7. It just makes things a little bit easier. We're going to be focusing on graphing next lesson, right? And then do 1, 2, and try 10 as well. All right, thank you.